Okay, well, I want to welcome everybody to the Software-Defined Networks for Quality of Service. My name is Pascal Menezes. I'm a principal at Lync at Microsoft. And I've been driving this program for about a couple of years. And I'd like to introduce Manfred.
Hi, I'm Manfred. I'm the Chief Technologist for UC for AG Networking. I'm part of our Advanced Technology Group. That's our CTO office, kind of driving future strategy, vision, going forward across what we're doing, real-time multimedia and partners. I've been working with Microsoft Lync, prior to being Lync since 2008 in the OCS days, and been a tremendous partner. Love seeing how we grew up from being an IM platform and a peer-to-peer calling, now being the leading enterprise voice replacement platform. And that brings us to some of the challenges we're seeing.
Yeah. So let me go through the agenda here. So we'll cover off, the issues and why we're doing the SDN, what's driving all of this. A little bit overview of the SDN API. How many years was at the session is it Tuesday's morning? That was the one session only about the overall SDN. Okay, 2 people, good. And then we're going to go talk about QoS, how we automate QoS, quality of service, using SDN. And HP, Manfred will talk a lot about HP's networking solutions around this. And then the path to how to get to SDN, full SDN. So let's make it interactive, and have fun with this. And let's just see where we go.
The recording is so if you could please come up to the mic when you have a question, that'd be great. If not, it's not the end of the world.
Yeah, and we're going to make it interactive, so we'll just take turns on this. So what drove all this is we've been finding that with deploying unified communication Lync, we find the majority of the issues have to do with networking issues. So users complain, and we find that during the complaint, when we do the investigation, we find that networking has a big part to do with that. And about 68% of all the user complaints we're finding to be network issues, related issues. Quality of service being one of the key parts to making sure you get right end to end, and we'll talk about the complexity and issues. Legacy networks have poor visibility in Lync because Lync is encrypted. We use encrypted in signaling. We use encrypted in the media. It's very difficult to really understand what's going on, and you're kind of blinded by that. So another reason. And obviously, we'll talk about quality of service being very complex. Anything, Manfred?
Yeah, one thing I'd like to add is things that the network used to do. We used to do things like deep packet inspection. We try to do heuristics, how to identify what the traffic is. But that's not possible anymore because it's encrypted. And on top of that, some of the techniques that networking folks used to do is create access controls, or ACLs. And that we would do to define what we incorporate into the application they're running on. Well, Lync, by default, uses ports 1,265.535. Well, that's pretty much the entire port range. Okay? So if you do that, almost any application that's UDP-based will now get better performance, which is clearly not what you want. And we'll highlight in the subsequent slide how some of the techniques that network engineers and system administrators are doing to define group policies or ways to try to make this work. But the bottom line is they're complex, they're easily broken. And but once they're broken, it's even harder to figure out what's going wrong. Because the problem with it, it's an intermittent problem. Right? Connectivity issues are fairly easy to diagnose. You either work or you don't. But when you've got an intermittent problem, maybe it's only happening mornings between 8 and 9 when certain traffic is happening on your network, or maybe in the afternoon when you're doing backups. And so when a problem is intermittent, it can be very difficult to troubleshoot and identify. So with this API, we're really bringing new visibility to the network. Sorry. Thank you. We're really bringing visibility to the network infrastructure to allow it to, the network administrator to automate what's going on and see what's going wrong.
So just bear with me for people who have seen this before. The bottom line is we want the vision, SDN, we really think of it as software defining the network. And SDN can come in many kind of flavors. But in essence, software-defined networks, we really want the networks and the applications to play better together. So unlike today's model of a ships in the night, application just dumps packets on the wire, doesn't have any clue about what's going on in the network, just hopes to get to the other end, if not retransmits. And the networks use all these deep packet inspection engines and all this cool stuff to figure out what's going on in applications. Wouldn't it be cool if the applications and network could actually just interact with each other? So that's really the key thing. So we're going to get more details of this, and I don't want to spend too much time. I want to get into the quality of service stuff. But please, if there's any questions, interact. Feel free to ask.
In the fundamental thing I want to get across is it's the difference between guessing and knowing. With the API, we truly know what's going on, and we can really provide a trusted model versus what we've been doing in the past is really kind of guessing. We think this is what this application is, and we think it should get this treatment.
Yep, good point. So really what's going on is if you look at it, I've been around in internet networking for almost 30 years now. And, way back in the 80s, we were doing, BGP, and back then we were doing RIP. And then finally went to OSPF and all. But at the end of the day, these protocols have been around for 30-plus years. Nothing's really changed. In fact, internet networking is still living, in the 20th century, where everything else has moved up. We're like decades and decades old in internet networking. And if you think about it, everything has distributed because back then processors, memories were slow, and so everything was a distributed protocol, distributed in the way of distributed intelligence. So every node was its own intelligence talking to other nodes, and they computed to each other, and a lot of complexity and all that kind of stuff. The other thing is we had a lot of network services built into these nodes, where you have security, IPS, IDS, a QoS was put on every node, access, and all that kind of stuff. So it's a lot of provisioning, a lot of intelligence was put into the network just so you can see what's going on in applications and do all these kind of network services. If you look at software-defined networks, it's actually taking a paradigm that says, hey, let's move, first of all, the services more centralized, because that makes a lot of sense with compute today and memory. And the second thing is, let's move those protocols centralized, and then basically let's have a way where we can program network elements almost in a very like instruction sets in a CPU, program them very real time, very fast, very granular, and we'll get into details about this. And this is what, OpenFlow is the first, southbound protocol to do this, southbound API. And so this is really the essence of SDN. But now on top of that, the idea that you can have these kind of applications that can actually give information, whether it be network service apps, and we'll get more details, or end user apps, and we're showing an end user app, like Lync at Skype, give information to these network controllers who have all these, or these SDN controllers who have this intelligence, have all this global view of what's going on. It's very powerful because you'll see it the first time that through an interface they can communicate to each other, and that can automate, simplify, reduce the cost of ownership, and have great experiences for end users. And that's really the essence. So what you get is there's a northbound API that's being defined for this application layer talking to the controller. And at the end of the day, it's about application-directed networks. And you're seeing the idea of an application can direct the network can communicate back with the application, and we'll go into more details about some of this stuff. Anything else?
And today what we're doing is the application is directing the network, but we see the vision as being well more than that. And we'll touch on that later on, is the ability now the network is able to communicate information back. In the future, we'll extend that to provide information back to the application and provide more intelligence. Things like call admission control, dynamic routing. So there's some tremendous use cases we can do that are very hard or almost impossible to do today that SDN will enable and orchestrate kind of in an end-to-end manner.
Right. So basically at this point, when we talk about software-defined networking, this is the paradigm. And really, we've been standardizing this. This is actually not, first of all, you're going to see, first of all, this is not a science project. This is this is actually happening. The API that we're talking about from Lync is shipping. This northbound API, this UCSDN API, we'll talk more in details. And we've seen this proof of concepts from last year are being delivered by HP. Aruba's doing Wi-Fi. They're shipping. Nectar's doing diagnostic, various scenarios. And we're driving this in the standards community. So myself, the UCI forum is the Unified Communication Interoperability Forum. I'm basically driving the UCSDN group, the technical group, as the chair. Manfred is on the board and actually also being a subject matter expert in that group. We're taking that and we're driving and we're liaison to Open Network Foundation, which is the SDN forum. And they're driving various standards, including the northbound API. And we're working together in a liaison agreement by us giving them use cases around UC.
And data models.
And data models. and basically the Open Network Foundation taking that and actually building out an API, and then giving back to us, and then we'd have a certification interoperability program. So, and you can see that, I'm also on the vice president of the Northbound API for the ONF, and HP's chairing that one with Sarwar.
And we also have somebody we picked up from Plexi who's chairing the data center group, because Pascal's focused on the user, which is really the branch and campus scenario. But we see that there's also opportunities in the data center. And the use cases, while they're very, very different, the data models and interactions and the type of treatment the applications want to get are somewhat similar. So there seems to be a good alignment along that. And we're getting some very good industry momentum around that. The other thing I'd like to say is, you stated that the API has been released from Microsoft. Likewise, we've been doing SDN and OpenFlow for quite a while. We started working with Stanford right around 2007. This was when it was still called ethane. We said, hey, some really cool research. We don't really know what we're doing with this, but we think there's some potentials around that. And so all of a sudden, one year, Google decided they, in their data center, started running OpenFlow, and they actually are using it in production to redistribute how they use their network radically from day to day, from hour to hour, based on their needs, and are getting a much better efficiency out of it. All of a sudden, the industry woke up. They're like, wow, this isn't just science fair anymore. This is real-world stuff. The difference is they're a very large company that can do a lot of what they want to do and have expertise, but how can we bring that technology down outside the data center? And our vision is that, the data center is important, but what's even more important is bringing it from the data center through the core of the network to the campus and branch where the applications reside. And we think that's a compelling use case. Because we've been working on it with these universities for a while, we've got the hooks in our ASICs, and we now have 50 miles of switches that we've been shipping for some time, and we've got over 25 million ports already deployed. And that's important, because this allows us to ignite this application. When we did the POC, got such a strong response. We're productizing this solution, and when we release it, it's something that customers will already be able to enable as soon as we release it, and not have to wait to do a complete hardware refresh.
Yep. Thank you.
And we'll touch on later on how we see SDN being applied in a hybrid manner. And we think that's the important part, is no one's going to do greenfield deployments in the campus and branch. How can you start using SDN incrementally to start deriving value for new functionality that's really hard to do?
So in this slide, we show you a very simplest view of, of the general SDN architecture. In reality, what's going to happen here is, what you get is, first of all, we talked about the southbound API, and today we're talking about OpenFlow, but there are other southbounds that are being showing up, but let's just focus on OpenFlow. The idea that the SDN controller has these different modules, for example, can do topology discovery, can do inventory, can do path computations, flow programming, set quality services, statistics. These are modules that will actually go ahead and send out, commands out depending on what that module is doing. So this is quite a lower level function inside the controller, right? The idea then is, what you want to do is you don't want an application at this point trying to talk down all the way down to the controller you're in, trying to have all that all these low level functions all the way in the application. You want abstraction. So these service modules, we call them network service functions, are actually modules themselves with intelligence, or they have kind of analytics in them, business analytics, or whatever you want to call it, analytics, and they have specific things they do. For example, in quality service, which is what we're going to focus on, we're going to show you how this module works with the controller, which then programs these network elements, and working with the application to get the requirements. Well, you can have the same thing for different use case, for traffic engineering, for security, for diagnostics, calling down to the controller for these different modules and then sending it out. So these are core APIs, northbound APIs. They're used by the same, by different services, but using the same APIs or same interfaces. Yet this interface is just abstracted just for the application of UC. So I wanted to show this because this is really the architecture model. And what happens is you can actually run these. More likely, what will happen is you can run them, decoupled from each other, and and it's a decoupled model, or you can actually have them all integrated. And more likely, you'll see controllers add value by having these network service function modules, layered inside their boxes, or part of the boxes, and one could live on another server, but yet communicating as one logical entity.
And the thing that's really important by having, say, the SDN QoS network service, the Lync application doesn't need to know topology. It doesn't need to know where are my branch sites, what is my link capacity, how many links do I have. That's abstracted for it. The UCNC application can request high-level functions on, I'm trying to make a video call, I need this much bandwidth, and here's the detailed information about that call. And then the network services can automate the programming to the controller of that, and that allows us to innovate and drive much more innovation in the application layer, because we don't want to have application programmers know detailed network topology.
That's exactly right. It's all about abstraction, layer abstraction.
You had a question?
Well, is this a solution interactive with IMC? We actually have IMC.
Great question. I'll tell you what, let's hold off on that question till later on. At a later point in the presentation, I'll try to remember. If I forget, do bring that up. Because SDN is important, network management is also important, especially in a hybrid environment. Okay? So that was a very, very good question. I'll bring that up.
Okay. So let me just go over what this Lync SDN API is. It's actually shipping, and we'll go into the details. I'll try to go over it briefly because I know there was a session on this in more details. But basically what happens is you have a Lync environment. You have two UC endpoints, Lync UC endpoints. You have these network elements, intermediate network elements throughout the path. You have a network controller, in this case an SDN controller. And what happens is signaling starts up, and you send a SIP, signaling to the server to proxy and find the destination. And so the server finds the destination. And then finally, media starts up. So this is a standard trapezoid kind of model from SIP. What's different now, as the media starts up, what we call early media, just at the time the media starts up, sub-second, we'll send a web service event out to an SDN controller or a network controller, in this case HPs, for example, and we'll send it out and saying that there's a dialogue that started right here, and here are the attributes of the dialogue, including the IP addresses involved, what's the SIP URI, what's the port numbers being used, if it's protocol type, what kind of media type, voice, video, data, what kind of codecs, bandwidth they expect. A whole bunch of richness of attributes show up here. And then if the call moves from voice to video, we'll do an update of that, or when it ends, we'll do an end of that. And various kind of call flows we can support with this model. So this is really what we call the construct is a dialogue. It's a start of a session. It's a start of a dialogue, or in this case, the end of the dialogue just ended. So Joe called Bob, start of a dialogue, finish the call, end of the dialogue. Or if they go from voice to video, it's an update of a dialogue. So that's a construct you want to remember. So that's one part of the API.
And if there's a multi-party call, you get multiple connections, because from a network standpoint, even a bidirectional flow looks like an audio call in both directions is really two separate sessions. They're really uncorrelated from the network standpoint, but this allows the network to now understand how the different flows are flowing.
Right, including, so if you took like an MCU, each session would have this start dialogue for each session, yet there would be, inside the attributes, it's belonging to a group, the same group. So it's a multi-conference going on. And so then what happens is the network controller now runs that logic, in this case the QoS logic, which we haven't gotten the details, and it starts programming all the elements for QoS. In this case, the QoS scenario, or it could be for security, but in this case, it's QoS. So in the controller has that, if you remember that diagram, has that intelligent, that analytical layer, that network service layer. It's inside the controller, taking the API, calling low-level functions, and then running out southbound APIs to actually program it. And these are real-time, like CPU instructions, but these are done on the network elements. So this is the essence of that. The next type of construct of the event type is the idea of a quality update event. And if you can remember these two constructs, it will really help you with now the follow-on discussion of how all this works. So like we had before, signaling went through. Oh, this
is correct.
No, I think that should not have come up yet, the event. Anyways, this is an older presentation. Okay, so bottom line is that the signaling happens, and at this point you have an error in the media, and at that point this would pop up that there is an actual event problem, that there's basically a quality problem, and we're getting a degradation of that session, and it could be delay or jitter, or it tells you what it thinks the problems are. So we have two types of events: session kind of events, and what we call quality update events. What's going on with the session? What's the quality of the session?
And we get that for all sessions at the end of the session.
Yeah.
And this is information that the voice or the application person always had, but in the majority of organizations we get involved with, there's a separate person running the network or a separate group running the networking. And invariably the problems we hear is the network's slow. So there's finger pointing. It's the app, no, it's the server, no, it's the endpoint, no, it's the network. And so the network guy never had any good visibility when there was a problem. By getting this update as part of it, we can now embed it in both IMC, as you talked about, which is what we're doing, and into the SDN application to use it to provide visibility on what went wrong, and also going forward on what we can do to maybe optimize and enhance the experience dynamically. And with this information now, the application knows virtual information. It knows IP addresses, it knows users, it knows what they're trying to do, but it doesn't really know topology. It doesn't know where these IP addresses really live. It doesn't know what port they are. It doesn't know what network they're traversing. The network, on the other hand, knows topology. It knows flows, but it doesn't know what it's really doing. And this is really bringing the two together and allowing to bring unprecedented visibility to the network engineer to be proactive, to solve things, and to automate things that he had to manually do before. Okay? And that's a really different way of looking at it, because when he sees a problem, he now knows what two endpoints on the network are causing that problem, and he can now do a path analysis to figure out where along the path things might have gone wrong.
Right, perfect. So one of the things I want to talk about is, so today the Lync SDN API version 2 is out. We started with 1.0 last year, the Lync conference. We would call it network diagnostic, because that was our first scenario. We now call it Lync SDN API. We have many scenarios coming around, securities coming out. We have diagnostics. We have Wi-Fi's going on the next session over here with quality of service, and we're expanding the scenarios. You need to install the APIs, this module, and it works on Lync 2010 and 2013. You install it on the front end. You download it. If you search Lync space SDN API, you can actually go ahead, download it, and you can install it on the front ends, and you can start playing with it. It gives you the schema and all that kind of stuff. Obviously, it doesn't do anything unless you actually work with people like HP to actually consume the API and automate it. Now, one thing I want to point out also is that we work with partners to continue to advance it, but you do need to install what we call a little piece of stub code on the front ends. This Lync dialog listener sits on every front end and then takes the information from the messages coming to the front ends and then sends that into an SDN manager aggregating kind of hub kind of unit. And that's a logical entity, could be running on front ends or another server. This was covered in the all-up strategy session on Tuesday, but I don't want to get into it. But if you want to know more, just come see me. I also want to point out that what we've now done with this API and this QoS, if you've ever deployed Lync before, you had to set up QoS on Lync and the endpoints and the servers, because out of the box it didn't happen. And you had to go specify port ranges and what's the markings to put up and all that kind of stuff. Very expensive. And then that's not even half the issue. You have to go into your network and make sure there's no remarking happens and that the markings match end to end and in every branch and every site and Wi-Fi. And you're going to see that's expensive. Expensive to operate, expensive to maintain, expensive to provision and start up. So the goal of this at the end of the session is all of that goes away and it's completely automated. So that's what we're trying to do. So let's see if we can articulate that. So I'll give this over to Manfred. And
we'll be interactive on this.
Yeah, that's fine.
Okay. So the one thing is why does Lync in real-time traffic need different treatment? And it's because voice and video has very strict requirements. TCP traffic can retransmit traffic, and TCP, which is typical data traffic, tries to get data from point A to point B as fast as possible. So it'll consume the network and kind of clog the network up, but voice and video is very regular traffic. Voice actually has a very small bandwidth, only 100 kilobits, and if you compress, only 30 kilobits, but it will not retransmit packets. So if there's any packet loss, can cause audio problems, especially when you have multiple lost packets. So the biggest thing is you need to make sure the packet loss is low, and you want to try to minimize the jitter and delay. The codecs these days are smarter codecs, and they will mitigate some of the packet loss. But we'll show when there's congestion, you tend to have bursty packet loss. So even on a network that, say, only has, if you monitor a network, might only have a 5% packet loss, sorry, a 5% utilization, because you're monitoring, say, over an hour, or you're monitoring over half an hour, there's something called microbursts. So in networks, because of the way the TCP traffic works, if you're downloading a PowerPoint, it will consume as much of the link as it possibly can. So you have short spikes of high traffic load, and that'll cause multiple packet loss. The codec itself will try to mitigate that, and the codec can do a good job at handling random packet loss, the kind you see in the wireless network, or the kind you see over in OK network. But when there's congestion, Pascal has some slides later on that shows what happens. You'll have repeated packet loss, and the codec cannot suppress that. And the way I liken that is, you know, QoS is like the carpool lane. Okay? When there's traffic on there and you can get in the carpool lane, that's great. And the codec is like a four-wheel drive vehicle. The codec's great, and you can go off roads, but why drive off roads across the entire country? You take the freeway for as long as you can, and then use the off roads when you have to. And that's just like what we're doing with Lync. You want to run the Lync traffic over your MPLS network as much as you can, and then mitigate running it over the open internet or over public networks, because that's where you'll run into problems randomly. The other thing is, when you're pulling video, be aware that video tends to consume 10 to 50 times the capacity of voice, so you want to queue video and voice traffic separately. There is no hard guideline on what QoS policy should be. Different organizations sometimes have different needs for that, but this is kind of the IETF guidelines, and this aligns very well with what HP networking does, and it aligns almost exactly with what Lync does, with the exception of maybe desktop share, not desktop sharing, file transfer. There's not complete agreement whether you're using, say, CS2 or AF21, but effectively it's about the same thing. The most important thing you need to do is that the order of priority is the most important. And voice and EF is pretty much standardized across the industry. Video and interactive video is very well standardized as well. Most of the vendors have standardized on AF41. And what you'll need to make sure is when you have a service provider that you align with what you've agreed to with a service provider with those policies. And that's an area where you can have some issues. The other guideline is don't mix TCP traffic with UDP traffic. So sometimes people think video is video. Well, YouTube video is not real time. Okay? The reason with YouTube video, if you don't have enough bandwidth, you'll get a buffering. It's because it can retransmit and it can send more data. With an interactive session, you'll get severe pixelation, audio issues, so they're very different. Okay? You don't want to mix regular video, like YouTube streaming video, with interactive video. Those can be run as either a best effort or maybe as an excellent effort. These are the guidelines that Lync provides, and if you notice, the audio, video, and signaling are the same as what we recommend, and there might be a slight difference between the app sharing and file transfer, but it's not that big of a deal. And the reality is this does vary from organization to organization and from service to provider to service provider. The important thing is these have been fairly well standardized.
So I'm going to walk you through a little bit of a QoS tutorial, just to make sure we're all on the same page. How many people really are experts in quality of service? Good, okay. So
do you want to cover these slides? Because we have no idea what these slides are about.
Sure. No, just joking. So what we're going to show you here, this is a typical node, network element. On its link, it's got its output link, it's got its input link. They have a scheduler, weighted round robin, weighted fair queuing, all these various mechanisms. And then you have, these queues. And in a best effort queue, you just buffer up packets, right? And then in a CS class selector 3, for example, or AF, AF21, 41, you have different drop zones in the queue so that packets, depending on their markings, have different drop preferences, right? So this is kind of ideas of random early discard kind of models. Also, you have a committed rate that you're defining to that class of service. And you want to give committed rates so that one doesn't starve everything, potentially. So you break out the actual output queue into some committed rates. So you give maybe 10% to EF and some 25% to AF and so on, these different things. And so this is standard kind of diff-serve, kind of how people deploy a diff-serve model. We're going to focus on EF and why EF is so important. You're going to see in the old VoIP world, because UC is not VoIP. UC is a much rich collaboration communication than just voice over IP. But voice over IP, in the old VoIP world, the reason that this became so important is this exact EFQ is it has to emulate a wire. You do not want a jitter, because if you have buffers, you're going to have jitter and you're going to have delay, because this could sometimes queue up or shrink, and so you get jitter, and then you'll have delays also included as hop by hop by hop. They include delay. So you really want to emulate at least a one packet buffer kind minimal in your EFQ. And the goal is to have this emulate like a wire so that your ingress rate must be less than your egress rate hop by hop by hop by hop. So this is a very important rule of EF, is that you're provisioning hop by hop by hop to emulate a wire as you never get congestion. Therefore, you never drop a packet. Therefore, your ingress rate is always going to be less than your egress rate. Okay? So that's the rule of EF.
And I guess the one other part to add in there is if you exceed that, it's not the last call that suffers. Let's say you can handle 10 calls across your link. Let's say you got a 300K capacity and you're doing 30 you got 30 kilobits call in your, times 10, so that's 300K. If you add the 11th call, it's not the 11th call that suffers. All calls suffer.
Yeah, I was going to
and
go
that
with
knee is very sharp. It's a very sharp knee. So maybe at 11, the coda kind of can mitigate that. But when you go to 12, it becomes unusable.
Yeah, I was going to go through that.
Okay, my apologies.
That's okay. So basically, you see there's 3 sessions running. Everything's fine. The ingress rate's less than the egress rate. The hop by hop by hop. 4th guy comes on, and then what happens is packets start dropping, but they don't drop in the last guy's session only. They drop randomly, and everybody can get affected. So this is a big problem. So we've known this since deploying voice over IP when we went from TDM voice to voice over IP. We've known about this, and so the general model has been, in order to avoid this condition, is to have a model where you actually have VLANs associated for voice over IP, and when the traditional model was to have a static phone that all it did was spit out voice over IP packets, you could have that assigned with 801X to a VLAN. No one else could plug to that VLAN because it was 801X authenticated for that administrator and only for the voice administrator. And the data, when he'd have his own VLAN and he'd get remarked, whatever he spit out in markings wouldn't matter. He'd get remarked the best effort. And so this was provisioned really nicely end-to-end. All this was set up for quality of service, and life's wonderful. And what you get is a nice, secured quality of service model that EF just works brilliantly. Any questions?
And we really haven't had any issues for the last 10 years running this. So the issue is once people started deploying soft phones, they were kind of surprised that there's audio quality issues starting to happen. You know, we've never had issues with an IP phone because it was secured. The phone auto-discovered the VLAN. The QoS was hard-coded. And then go to the next slide. You know, you'll highlight how the same PC can do voice, video, desktop sharing, any other type of application. How do you recognize that? But even worse, many OSs don't enable QoS by default. And even if they did, we find many network administrators simply don't want to trust the endpoint. Maybe if you have corporate issued laptops, you can control what they're doing and you can lock down what the users are doing. But as users are bringing in their own BYOD devices, good luck turning QoS on it, at least today. Many BYOD devices don't offer facility to turn on QoS. And if they did, I liken to what I see happening on the carpool lanes a lot, is people simply put a dummy in next to them in the carpool lane, put a wig on it, and put some makeup on, and drive through the carpool lane. So as long as they can get away with it, people like to abuse the system. So we find that administrators often like to lock things down, and that starts becoming very, very difficult. Or if you try to trust the endpoint, it can be very hard to make sure it's all configured correctly.
Plus, it's a great denial of service, area. So if you get any malware, they'll start spitting out packets with EF packets. So this is well known. Like you talk, network administrator remarket, don't trust data. So on the other slide. So what happens is now this data tunnel, like you said, is spitting out voice, video, data. It's all converged platform. And on top of it, you have mobility because you have a soft client running on a smartphone, and he's moving on Wi-Fi, and he's moving all over the place. So Manfred makes a very good point. This is a big issue for UC, and you're not going to have VLANs, and it's a BYOE device, not even domain joined, right? So you're not going to deploy certificates and all that kind of stuff. It's a nightmare. So
in the application on the soft phone is typically written by a different vendor or different partner than the hardware manufacturer. So trying to get that talk to the OS, good luck with that, right? The application vendors don't want to know, are they talking to an Ethernet driver? Are they talking to a Wi-Fi driver? They just want to write some high-level policies.
Right. So what you're going to see is this remarking, this untrusting of UC is a big problem compared to VoIP with a specialized handset, specialized connector, this multimodal coming out of one connection, of voice video data and moving at the same time. Top problem. So what we're going to show you here is the complexity of automating QoS and traffic engineering. And Manfred, do you want to take a walk through that? It's pretty wild, and it's expensive and hard.
One approach is you can enable DSCP on all the endpoints and make sure you've got that configured, which can be quite hard. So the other option is you can start locking down UDP port ranges, but what you need to know is that Lync, and especially if you're trying to coexist, you have to make sure that Lync now coexists with your Cisco Call Manager or your Avaya, which also you may use voice and video, and you don't want those ranges to overlap. And then you have to go in the Lync policy server and figure out, am I doing client audio? Am I doing client video? Am I doing client desktop sharing? Am I doing conference calling audio? So you have to provide different ranges for all of them. Decide, do I have enough? How many port ranges do I need? Is 5 enough? Is 10 enough? And you have to make sure they don't overlap. And then you have to hand that via SneakerNet or some other mechanism to the network administrator where they have to configure these ACLs. And if they get the direction of any of these ACLs wrong, or if they take 5048 and turn around a couple of digits, which I've seen happen plenty of times before, and they only get that wrong on one of the switches along the path, you've got some problems. And the problem goes on and on. If you try to do CAC, if you're trying to do some of these other things, it becomes very, very difficult. And we see people often throwing their hands and say, the pilot's working just fine. I don't see a problem, okay? Well, the pilot will always work fine because you're not really stressing the network during the pilot. But as Lync adoption grows, and it does grow, and one thing we've seen inside of HPIT's own internal deployment is in the past, I stopped using my phone, and I saw many, many people stop using the phone because the phone is pretty much a useless device, or at least the desk phone was a pretty much useless device. My cell phone was so much easier. With Lync, between presence, I can always find somebody. I'm never busy. I usually start IMing. We do a couple IMs back and forth. But then what we find is, this is tedious. Let's start doing a voice call. So we've seen that over time, our voice usage has gone up, and we're seeing the same thing for other customers as well. So you're going to see a growing adoption of voice today. And as the younger generation is coming up through the workforce, the video for them is important as well. And so the adoption will grow, and that will drive more bandwidth through your network as well, complicating this problem. So as the adoption grows, you will start having problems with audio quality, and that's exactly when you want to ensure that you have a good user experience. If users have a bad experience 2 or 3 times in a row, they're going to stop using the tool and switch back to what they're used to. Right? You want to encourage the adoption, not force the adoption.
And then the other thing I want to mention is that, this is yours. The other thing I want to mention also is that in a consumer UC environment, it doesn't matter. You don't care about QoS. You're running the internet. There's no quality service, and people are not really paying much, and they don't expect much because they're getting it for free. So
good point.
On the enterprise version, this has to be as high quality as your TDM voice. It's got to be reliable, always up, high quality, high fidelity. I mean, users don't, it's VoIP, UC, I don't care. I just want it to work the way my regular landline works. So this is very important, and you cannot get there without quality of service. And it's not just quality of service on the endpoints, as we've talked about. It's quality of service on the network, end-to-end. It has to be perfectly aligned and with the right markings. And if there's one place marked wrong or stripping markings or changing markings or doesn't understand markings, that's the part that's going to be affected. And this is across all your branches, it's across your Wi-Fi. I think I've said this. So it's a lot of work, and this diagram shows this. I think this is yours now.
Yep. So let's give you, I want to give you a little demo. I believe this is the demo slide here, yeah.
The UCNC SDN application automates network policy in a dynamic fashion unlocking the full potential of unified communications and collaboration solutions through an enhanced user experience. Take, for example, two employees attempting to collaborate via Lync using application sharing. On the top left, we have the user James, and on the bottom left, we have the user Linda. James initiates a call to Linda and then starts sharing an application. As you can see, Linda's user experience is significantly delayed and not synchronized with what James is sharing. This is not a problem with Lync, but rather an issue with how the Lync traffic is handled across the network. This poor user experience is all too common with today's UC&C solutions. In fact, users are not only frustrated by this, they have come to expect this type of experience as the norm. The reality is that poor application performance is a drain on productivity and limits the power of unified communications and collaboration solutions. On the right-hand side of the screen, we have the HP UC&C application in a disabled state. When we enable the application, the user experience is instantly transformed. Now both users are seeing virtually the same information at the same time. The UC&C SDN application has taken call intelligence from the Lync server and used it to implement OpenFlow rules via the HP Virtual Application Network's SDN controller.
So we've gotten such strong response from this proof of concept demo we did a year ago at the ONS, Open Network Summit, that we're productizing the solution. And we're also integrating this into our IMC platform because we believe that there's importance of providing monitoring for the legacy network, providing the monitoring for the hybrid network, and automating QoS in a hybrid solution. So let me drill into a little more into detail what we are doing here and how this works underneath the hood. So we got Lync up here, and we have the HP networking band, which is the virtual application network controller out here. And then we have our UC&C SDN application up here. When user James contacts Linda, the signaling flows typically a different path than the media. The signaling is encrypted, and so is the media, but the Lync server knows all this detailed information. The Lync server then, via RESTful API, sends a dialog start event with the user identity, so we know the username, the URI, what they're trying to do. You know, they're doing voice, how much bandwidth it's requiring, what the codec type is, and all the IP addresses and port numbers. But the networking controller, you know, it doesn't know any of the topology information, but the controller over here knows what ports they're on. It knows the MAC addresses. It knows that information. So what the controller now does is it programs the OpenFlow rules only on the ports where those users are connected to, dynamically, only using up hardware resources for the active flows and preventing somebody from hijacking or misusing that marking. For example, in here, if we have a malicious user sending EF packets in or sending a high bandwidth packet stream in here, this switch would simply remark that back to a different policy and give it a best effort treatment. And only this application now is dynamically running. And then at the end of the call, the dialog stop event would come and we would tear it down. Or if something went wrong and it would time out, we would just simply age out that flow at some point in time. Any questions on that? Okay, let me drill in a little bit more, kind of to show how that actually works underneath the hood in the network topology diagram, because a common question I get is, okay, I get it, how you're using it to mark the traffic at ingress. And the reason you want to do it at ingress is QoS is really only as good as the weakest path. You want to make sure that QoS is flowing end-to-end across your network, both across your wireless, across your WAN link, and across your core infrastructure. Did you have a question?
Yeah, are you marking all of the traffic from the endpoints or just the voice code?
Just the applications that Lync notifies us that are relevant for what the user administrator policy configured. So we give the user administrator some template. We default it so that in most situations they don't need to do anything. But the type of things they would likely want to do is voice, video, and desktop sharing should have higher priority. So we only mark the traffic for those unique flows and only that unique port number, not even a range anymore. So yeah, it's per flow and dynamic. So here's an example. Let's say we had two users using a soft phone, and they're on a PC that's out of the box with QoS disabled and no markings in the endpoint. The dialog start event comes, and then via OpenFlow, we're setting an action that says, for these flow, do this action. And OpenFlow supports a number of different actions. One action would be drop. Another action might be modify the packet. In this case, we're saying modify the DSCP, so this is the layer 3 inside the IP header, the QoS field inside the packet, and we're changing that. And now that packet can flow throughout the network. So notice what happens now. From the PC to the switch, we can't change anything, but as soon as it hits the switch, we've now changed the contents of that header marking, and now the network can honor throughout the network. And this is important because the rest of the network statically has been provisioned for the last several years in most enterprises to support voice, and the MPLS customers have gotten MPLS agreements that says EF gets this type of SLA. This now allows us to have a trusted model where the network now is link aware, and it's enforcing trusted per session dynamic policies. So there's two reasons we want to do it at the end. One is you want QoS to be end-to-end across the network, and the other one is to make sure that we don't exceed hardware tables in our ASICs, because OpenFlow is fairly new, and you can't support millions of flows in hardware switches today, or at least not in a very cost-effective manner. On an access switch, you're likely only going to have 24 or 48 ports, and how many users can start up how many link sessions? It's a fairly small number. These access switches tend to have, at least HP switches have on the order about 4,000 flows, which is well more than enough you can ever run into end users running. So even in the distribution layer, this will work fine. But in a large core network, that's clearly not enough flows to do this granular marking. So what we want to try to do is drive this intelligence as far out to the edge of the network and provide this kind of intelligent functions at the access layer. Do things like network access control, which has been really hard. Do things like IDS, IPS. Do things like redirecting traffic for diagnostics at the access layer. And at the core of the network, be more of a high-performance, simple network, and have that more static policies, at least for the next several years. And this allows us now to have an auto QoS for link that's secure. And the important thing is this allows to run it in a hybrid model, okay? Because no one's going to start ripping out their entire network and replacing overnight. And this is really an important part, is the hybrid model allows enterprises to start deploying this in a manner that doesn't introduce a lot of risk, because if this application for some reason broke, you're no worse off than you are today. It simply would run as best effort. And then going forward, as a subsequent things, we want to have the SDN controller push back to the application. For example, the kind of things we can start doing is, rather than blocking calls, we know topology. Let's say we started let's start a video session. Rather than doing a high-def video session, the network might come back and say, you know what, there's not 4 meg on this WAN link. Why don't you do a compressed call? And we can now automate things that in the past has been very, very difficult to do in the network. Yes?
Some companies transition away from IP MPLS to just internet only, like E10 or E100.
Yes?
And so you pretty much only have internet, and it's the best effort, but you just hope that you have enough bandwidth. How does your model fit in, or if does it fit that?
Okay. Well, what you highlighted is a pretty good question, but we're not quite seeing that yet where they're only going to internet traffic. What we tend to be seeing is they don't want to keep running all their traffic through the data center, because it used to be all a hubs and spoke model. So we used to run all the traffic to the data center and then back out, and you're paying twice for the bandwidth in that case, right? You're paying it from the branch to the data center, and then you're paying again for this really fat pipe out to the internet. So most companies, or most enterprises or mid-sized companies, what they're doing is they're getting a DSL, they're getting Ethernet service, they're getting something for WAN, but they still are getting an MPLS. But use the MPLS for important traffic, use that for voice, use that for video, use that for critical, but then use the internet for bulk traffic. That allows you to save your cost on your networking. And here's another example of what SDN can start doing. It can start using the policy that says, I can do dynamic routing. So networking today often does policy-based routing in the WAN routers, where you put in specific routes that says, based on this code point or based on this IP address or based on this ACL, I send it one way, other traffic the other way. So this allows us to take advantage of that mechanism. Or even further in the future, let's say you have a DSL, but you have a 4G network that you can dial up. Maybe the Ethernet WAN or Ethernet Internet works well 80% of the time. Let's say it works 90% of the time. Let's say we get a notification that we got poor call quality. We could now reroute it to the 4G network, which is more expensive, and determine which one's running better at that moment. So it allows us to do things that today in IP routing are almost impossible. It allows us to kind of violate routing principles because the controller's making a decision. It's not based on IP addresses and routing tables. Yes?
So this works well with like an internal network type of deployment. So with nowadays, a lot of people are not commuting to work with a highly mobilized workforce.
Yes.
How are you guaranteeing or improving that model in that case?
No, that's an excellent point, and I was trying to make that example earlier on with kind of like four-wheel drive vehicle, right? Drive on the freeway for as long as you can, use that carpool lane for as long as you can, and then only hop off for the last little bit. So what we find is, for example, with HP, if we're going to call from North America to Europe, we're not going to run that over the internet. If you're going to run that over the internet, over that large of an internet, you're likely going to have a poor experience. Run that over your core network. But then if you're running a little bit over the internet, you're likely going to have a pretty good experience. Okay? The other part is with the diagnostic API, if you're having call quality issues, at least the network administrator can find out which calls are internal, and those should always be near perfect call quality. And then you can identify which calls are over a wireless network. Those might have okay call quality, and which calls are to a remote user. And in that case, you really can't do anything from an IT organization. Use a support organization can say, are you at home? Are you on wireless? Well, maybe you got what you got. It's better than your cell phone, but maybe you should be using some other mechanism if it's an important business call. Hopefully that kind of answers your question. So the reality is no, we can't solve everything, but I think what we ought to be doing is engineer for as much as you possibly can throughout your network whenever possible. And do it in a manner which is simple and not complex.
You guys, when you talk about the highway type of idea there, say your VPN concentrators, do you guys remark your traffic coming in? So like you're going to say, on the internet part of it, that VPN tunnel is going to be best effort, but after we hit the concentrator, we're going to mark it coming into the network or not?
You shouldn't actually even be running voice traffic through a VPN concentrator. You're going to have serious problems. So we actually ran into this problem in HPIT and a lot of customer deployments. What you want to be doing is the Lync media is encrypted. So there's no reason to run it through a VPN concentrator. The VPN concentrator is your biggest bottleneck in your entire network. You're lucky to get a 200 millisecond hop through that thing. So what you want to do is have a split tunnel, and the endpoint should be running only data traffic through the VPN, and everything else should be running through the edge services. And at that point, we can start marking the traffic as soon as it hits the enterprise network. And
I think that's what you're trying to allude to. Well, I mean, the bottom line is, the whole idea is to mark it as it enters in the autonomy that you control, right? You can't control the internet, you can't control parts. So, again, this API in this use case is about automating costs. And there are another use case around diagnostics to say, okay, you're having a problem. We see you're coming from home and you're transferring to the internet. We can see in that everything from the edge of the enterprise good is working fine. It's either the internet or your Wi-Fi at home. So today we don't even know that. We have no clue about that kind of stuff. So this is very important. So. I think, is that relating to the question you asked before about the concentrator? Is that what you're saying?
I haven't seen a case study, but I know with HPIT internally, when we were running through the concentrator, that was a cause of a lot of the problems. And whenever we could, we tried to do one or two things. Make sure to run it through the edge services when possible, or at least make sure you have a concentrator that's not overloaded. Because if that concentrator is overloaded, it'll buffer, do a lot of buffering, and you will get problems, right?
Because a lot of times you're encrypting if you're using IPsec or SSL. So you don't want to double encrypt is the issue. And the thing is, Lync has built out its own edge servers using stun and turn, its edge proxies, to do all of that stuff. So you should be using those services. They're designed for running our voice and video. And
No, I completely agree.
yeah.
It's just that, if you guys had some type of white paper that shows the difference and shows why it's necessary, it's easier for me to go to my security team and say, okay, look, here's the protocol, this is why we should do this, here's the effect that it has on voice quality.
Yeah.
Because we know that more people are going to be mobile, more people it's just going to, the problem's going to increase and increase.
So there's a center of excellence team that maybe if you give me your card, I can direct you to them. They probably have a lot of documents and white papers on guidance with this.
The other thing you can try to do is make sure you have more than one VPN concentrator. The last thing you want to be doing is, let's say you've got a global company, do not run traffic from Europe through a VPN concentrator in New York, and only do that if as a last resort.
And that's the same thing with the edge servers, too.
Right, exactly.
Yeah.
Right. You don't want to be, because otherwise you're hairpinning that traffic potentially multiple times across intercontinental or transcontinental, WAN link. So, media flows best in the shortest path and not running it through unnatural paths.
Yeah.
Any other questions on that?
I just have one, if I might, which is, given that the Lync front end has to talk to the cross controller, and the cross controller then has to program the switches to what have you, how long does that take?
Well, it's pretty quick, okay? And the good news is we highlighted earlier that the early media may actually flow.
Actually, there's a mistake. It should be best effort being best effort on the inside. So.
Okay. But in here, the early media could actually be flowing beforehand. And typically when it's ringing, by the time the person picks it up and they say hello, hello, a couple seconds went by. And so even a very large network, you should be able to get this provision in a very fast amount of time. But if something goes wrong, it's typically not the problem. Once the media starts and people start talking, at that point, the QoS should be good and stay good. It's the users are frustrated after that point when it degrades, but not at the beginning.
And then the idea of OpenFlow is to do this very fast programming. But you're right. I mean, the idea is, would you have a centralized controller trying to talk to, you're in Las Vegas trying to talk to New Zealand or something? No, you're going to have distributed controllers. So the idea you're going to move to distributed controller models. So this is where it's all moving to.
But we did the math, even for an organization like HP, which has 300,000 users, and potentially every user has multiple devices, could be 1 million devices. The number of people making concurrent calls aren't really that high. So that, we may make overlapping calls, but how many calls per second are you making? And if you do that math of how many different switches that's crossing, the math works out very well. So it does scale to a very, very large number. You said there was a. I believe that's correct.
I think go back a slide. I think that's the mistake. Right, go back, right there. You start with best effort. Should be best effort on the inside, and then
thank
as
you.
you get.
You're right. I apologize. Yeah,
Yeah.
This is all red. This is a typo. These
Yeah.
are all best effort
Yeah.
here. When it went green, then it's correct.
Yeah, that's right.
Thank you. Yes.
Just a quick question. So those dynamic policies on the access and the distribution layer, what about on between the router? Is it like a fixed QoS?
Yes.
Yeah.
And so we're using kind of this is the model that's pretty well established today with VoIP traffic, and most traffic is recognizing the application is the hard part. Once we've recognized the application, enforcing the policy has been actually pretty straightforward. In HP switches, typically all you have to do is turn on QoS type of service DSCP. Okay, once you've turned it on, we've defaulted some pretty good defaults of how to map that priority to what queue. Okay, so that part's not too difficult. The one part you do want to make sure to do is with your service provider that you do get an MPLS agreement and that you align the internal DSCP code points to their code points.
That's right.
And different service providers, you might get 3 priority levels, might get 4 or 5, and it might vary across the regions depending on which provider you work with. You just want to make sure that they map accordingly. Remapping the DSCP, say at the WAN router, is typically not too difficult. You know, all the boxes allow you to say, hey, AF41 in my network maps to AF42 on theirs. You can remap that. The hardest part was understanding the application and trusting it.
Actually, we have 32 plants around the globe. We have an NTLS cloud, and we already defined the quality of service classes in the cloud, in the MPLS. So is there, well, by using this SDN solution,
It's very complementary.
can we just match what
Yes.
we see?
Yeah.
Yes.
In fact, you would take the policy from your MPLS and you would ship it into the policy of the QoS controller.
Yep. And
That's what you want. You want to match the markings.
what we'll have is one high-level global policy that allows, or we'll have a policy for domain that allows you to say what marking should voice go in. So typically you would put in EF and video would go into AF41, but if you have a different marking, you would just change that. So it's one setting you would change and it would just apply everywhere. So it really fits in well with the model you've already using today.
Yep.
Was there another question?
No, so just the SDN model is just not on the entire network. I mean, the dynamic can't be applied on the core network at the moment.
Yes, and I got a couple slides coming on why we're doing this, and this is really to drive adoption, because our belief is to get you to adopt this. Let's focus on a couple of simple use cases first to get you the confidence on this and show that it works, shows that it scales, and then add additional functionality. Rather than revolutioning the world overnight, we believe it should be a phased migration. Just like with Lync Enterprise Voice, I don't believe I've ever met a customer that says, you know what, I love this technology, let's roll it out to 30,000 users overnight. It's a great technology, but your odds of getting that right overnight are challenging, so why not deploy something in a manner where you phase it and get comfortable with it, and you can start this on one branch and then over time migrate to more and more branches. So where are we with SDN today? We believe SDN is really important across an entire ecosystem. You need to have the infrastructure enabled, you need to have a controller, and you need to work with applications. We've got 50 miles of switches that we've been shipping for the last 5 or so years. And what we find is when people are doing access switches upgrade, they expect on the order of 7 to 10 years lifespan off of them. So even if somebody's not ready to do SDN, say, tomorrow, ask them, what is your chance that you want to stick your head in the sand and not do any SDN for the next 5 years? I've yet to see a single customer that says, nah, this doesn't look interesting, this doesn't look relevant. So get yourself having infrastructure that's SDN ready. We have announced that we're going to do SDN on our WAN routers. We also have announced that we're going to do SDN on our wireless products so that we'll be able to extend this capability. We have an API SDK as well, so that we want to enable third-party developers, not just strategic partners, but make it easier for system integrators and others to write innovative applications on there. After my other session yesterday, somebody came up, could we use SDN for call recording? I scratched my head for a second. Absolutely. That's actually a really brilliant idea, because one of the actions is you send a unique flow down to the switch and you say mirror that and encapsulate that. So you could then send it to a remote server and send it to Wireshark. So we've demonstrated applications around security. So we've got some security applications doing IDS, IPS at the access layer, doing that at a school district, and we're doing it at HPO. We're demonstrating load balancing. We've got the Lync solution here. We're doing things with Verizon around virtual cloud. So we believe we need to demonstrate a lot of compelling use cases and to build this adoption on there. And we also have some design and implementation and educational services around there as well to help people get comfortable what SDN means and how to start deploying this. And then kind of going to the path of SDN, what people were asking is, how do I get to an SDN? The first part, we feel, this is already something we've been doing for the last 5 years, is we've been getting customers having an SDN-ready infrastructure. And this is really a way that is based on open standards and a very low risk. There's really no risk with going with HP networking infrastructure that has this future-proofing capability built in, and then running, say, a hybrid solution now that we're demonstrating here, and we're going to be releasing soon, that allows you to run OpenFlow in a hybrid model with legacy switches, routers, and other devices in there using this approach. This allows you to be application aware, reduce complexity, and is very non-disruptive. You continue doing what you do well today and add additional functionality. And then that gives you a path over time to support more types of applications and more functionality in native mode. And these native modes will be, say, SDN domains. So maybe you're doing that in the large campus, you might have an SDN domain. You might do that within one enterprise, have an SDN domain. But between domains, we will still, for some time, be running standard routing protocols between them so that you can interface with the rest of the world. But with inside your SDN domain, you won't even be, there's no need to run things like OSPF. There's no need to run spanning tree. There's no need to run any of this. We can now redirect packets and take advantage of all the links and do things like dynamic load balancing and very innovative things in that pure SDN domain. Anything you want to add to that?
No, it's perfect. Exactly right. Start with islands and then start building it out.
So really, it's about how do we have an optimized networking experience that's application directed, that allows you to eliminate complexity, ensures enterprise-grade voice and video, automates things where we can, and it provides visibility when things go wrong. The important thing is really in a way that we're driving that's multi-vendor, standards-based. You'll see other vendors promoting similar type of vision, but they're saying, hey, use our open source controller. Oh, and don't mind the protocol we're using. We're using this 1PK thing that requires you to use our entire network infrastructure end-to-end, but we're open standards, but as long as you use all our hardware. Okay? Really look at vendors that are driving open standards and multi-vendor, and look at ways that you can get this built in. We've seen plenty of vendors who are announcing OpenFlow, and they say, sure, but you'll have to buy new hardware. The current hardware is no good. You just got to continue replacing your hardware.
I think that's the end, right?
Yep. Did we have any more questions?
No? Did you?
I realize, this is obviously a Lync conference, but can you put other applications on top of that in addition to Lync?
Like what kind of applications? Like a video conferencing system?
Something, somebody else's video conferencing, Avaya or...
Sure. So that's what we're trying to define. We're defining a standard called UC-SDN. Instead of SDN for data centers and SDN for clouds, this is UC-SDN. And UC-SDN, we're standardizing through ONF and UCI Forum so that vendors like Avaya could do it. Like, whoever UC systems want to do that. Network vendors also can consume that API, this higher level API from UC, and then run the same kind of scenarios they wanted to. We want a standards approach. We don't want a proprietary approach. That's why we're standardizing this.
I mean, we could say, hey, we're only going to keep it for ourselves, but the reality of really gain adoption and really get excitement across the industry is to allow us to provide this type of automation and simplification going forward. And we're starting to see more and more devices connected to the network. And the way of doing things today on a box-by-box basis via cryptic CLI, I don't know how much longer people can do this. I mean, we're already having 3 devices on average per person, and now we're talking about the smart power grid. We're talking about the Internet of Things. We're talking about refrigerators being Internet connected. I mean, some things are ridiculous, but the point is there's going to be a lot more things connected. There's going to be a lot more devices out there, and we need to make a method where a handful of guys can deploy a large number of switches and simply make it run. We need to bring networking into the 21st century.
Yeah, so in essence, complexity is increasing. And if we don't get to automation, then it's going to affect TCO. It's going to affect the cost. Cost is going to continue to rise to support it. And you're going to have to pay more and more for people who are highly specialized. So the idea is we need to start automating to bring down that cost. We need to reduce the complexity to try to make it more simple to understand with the troubleshooting, setting QoS. We showed you examples in other sessions how hard and expensive it is to set QoS. So the essence of what we're trying to get to is have an application interact with the network. In this case, UC is best because it has long-lived flows, right? If we can do that, then we can start this automation process that gives a lower cost of operations and have greater agility. So you can roll out new services, you can do new things, and then finally have a great end user experience instead of this just throw the packets on the wire, hope it gets on the other end.
And to add on that, the one thing that I've seen is in the last year, I've seen more excitement, more interest in the networking space in the last year than I've seen in the last 15 years of my career. And the reason is writing embedded firmware and switches is extremely tedious and time-consuming, and writing a new protocol takes time. And then usually that requires a new model of switch because they required more memory, required a faster processor in there, and then you have to get the customers to upgrade to those new switches, and that's a 5 to 7 year life cycle. So the innovation cycle was incredibly slow. Okay? It took networking vendors a very long time to get new functionality out, while the software vendors were cranking and innovating. What we're doing now is we're taking and putting basic primitives into the switch, putting more capabilities into the ASIC, and then pulling some of that software out into the control layer, which truly is just a pure software application now. It's a Linux application, maybe a web application, and that allows us to really innovate and write more applications, and allows other third-party vendors to write applications that interact with the network, and allows us to innovate that much more rapidly than we've ever been able to do before. And I think that's really transformative and different. And going back to your question, that's also why the big cloud providers like Google and others, their data centers are becoming so large. They have so many servers they got to connect, and they're racking so many new servers and so many new switches on a daily basis that they simply could not do that manually anymore. So they needed some way to automate that, and that's where the SDN really was exciting. They've proven it, and what we're trying to do now is bring it out of these small islands in the clouds that only the elite can have, and bring it to, standard campus and branch networking from the end user application to the data center.
Right. Any other questions?
So for HP with your controller, how many switches are you managing per controller? I guess how does that scale?
It depends partly on what kind of application you're going to try to run. And initially, we're going to keep that number. The product's not announced. I don't want to go into those kind of things yet on the product. But initially, we're going to keep that number a little bit conservative. And we'll be able to increase that as we go forward. And it depends on what you're trying to do. This application itself scales pretty high. But let's say you're trying to do IDS, IPS, that might scale a little bit differently. So part of that model is how many services are you going to try to run on top of the same controller? And then also, how resilient do you want to have that be? Do you want to have a controller per larger site, or do you want to have a controller across several sites? That's the kind of thing we need to think of. So it's less on how high it can scale, but more what's the right architecture to ensure your continuity operation of your network.
When you guys release the Cisco 3650 to some of the SDN stuff, or have the potential to do the SDN stuff, are you guys, your controller going to be able to talk to the Cisco switches, or is it?
The initial release, we're focusing on HP only because we want to get something out and have it proven, and we know what version of OpenFlow and the extensions we have. But our intent is to start supporting other vendor switches out there as well. The key is they'll need to support OpenFlow and the right version and extensions that we support. We believe that's going to happen, but it may not happen in the next 3 months. Cisco has acknowledged that they've been behind, and they're starting to embrace OpenFlow. Or they said they're going to start embracing OpenFlow. Today, they're focused on 1PK and want you to use their proprietary mechanism. And the switches that they've announced that are OpenFlow capable are data center switches. So it's the 9K, it's the, I think it was the 4000. So right now, they're not focused in the campus and branch, but it's just a matter of time when they will. And at that point, we'll work, if they allow us, we'll work in interoperability with them. It's not always that they're open to working with us.
You need to close your ears, and I got to ask, what other companies are doing controllers?
So you'll see in the show, we've been doing this with Aruba for Wi-Fi. We're doing this for Nectar for automating diagnostics, can actually pinpoint exactly where the call failed in the network. And we're doing it with HP right now on Quas. There'll be new scenarios that we'll be working with and partners in security and so on, and we'll be adding new scenarios with our existing partners. We are building a large ecosystem in this area. The API, we believe, is very innovative, and we can actually, again, lower the cost, automate, provide agility, and make the end user customers, the deployments of Lync, be much more flawless. Okay, so that's the end. We are running out of time, so I'll be sticking around for some questions. Please fill out the survey, please. That'd be awesome. And don't forget, there's a link to the party tonight, so hopefully we'll see you guys there. And thank you for attending.